So let's pick up where lecture 5 left off. I wasn't here, but Rio Yokota, my postdoc, he tried to actually record the lecture, but he told me that among the heat of the moment, he forgot to press record. So we will post the slides, which had a lot of information, as a PDF for you, and you can use that to you will see there most of the material. Also, it is a material from the book, so you can also study it from the book on pages 38 to 52. Mostly what was covered in last lecture is there in the textbook by Post. And basically what it was is the application of hydrostatic formula to calculate forces on submerged bodies. So the first approach was simply a rectangular, vertically oriented surface. Then the next, incrementally gets a little bit more complicated. The next step was looking at a trapezoidal shape, but still vertically oriented, submerged in water, say. The next step was inclined surface, a circular vertical surface, but a plate, a disc shape. And there was another example of a trapezoidal reservoir, like a tank of water. Calculate the forces on that. And finally, the force on a curved surface. Those were the types of problems that were shown last lecture. So let's do a little bit of a now go back and look at a few sort of shortcuts to solve these type of problems, because you saw that to calculate the forces on a submerged surface, we really have to do an integral, right? We calculate the integral of the pressure times the area, the differential of area, and so we have to integrate because that area of an inclined or vertical surface will normally depend on the depth, h being the depth measured from the surface of the liquid. Now, one shortcut that you can use for geometries that are regular geometries, like a rectangle or a disc or something that very regular, is that you can calculate the total force on the submerged surface by multiplying the pressure at the centroid times the area. So this is the simplified formula for the force on a submerged surface. So for example, if we have the situation of right here in this picture, the surface is indicated by this little triangle that indicates that there is atmospheric pressure there. So suppose we have a, say, an inclined plate there. So this is our wall. And we want to calculate the forces due to pressure here. Of course, the pressure is acting on this inclined surface, always perpendicular to the surface, but the pressure is changing, increases as you go deeper and deeper in the water, right? So there's a distribution of pressure. So we can calculate the resultant force. Say the resultant would be some force acting on some point here. And this resultant force we can calculate by using the pressure at the centroid multiplied by the area. So the pressure at the centroid is, of course, let me see. No, let me be more clear here. There's an issue here that I need to be clear about, which is the force, the resultant force we can calculate using the pressure at the centroid, but the point of action of that force is not at the centroid. Okay? The centroid would be the sort of geometrical centroid would be somewhere, say, suppose this point here. This is H of the centroid. But the point of action of the force is not at that point. That's what I'm trying to say. Okay? So the resultant force, F, is equal to the pressure at the centroid the pressure is simply gamma of the liquid times H of the centroid, and if I multiply by the total area of that surface, then I will have the magnitude of the resultant. The magnitude. But the point of action is somewhere else. Is that clear? So the magnitude of F depends on the the depth of the centroid. Yes. HC is the depth of the centroid. The magnitude of the force depends on the depth of the centroid. But the line of action of F is not through the centroid. It is through what we call the center of pressure. You should have been introduced to that term last lecture. The center of pressure. The center of pressure is basically the point of action of the resultant of the pressure force. It's a definition, okay? So the important thing is not to be confused by the fact that the magnitude of F does depend on the depth of the centroid. The line of action is somewhere else. No, it's just trying to indicate that A, the area, can be a function of H. So area, for example, if you had a disk, the differential of area would be a little line, and as you move further down the disk, that differential of area is going to change. And that the key, of course, is to find the relationship between the differential of area and H if you're going to do an integral, integrate properly. Yes. The geometrical center, just a geometrical center. So, you know, it's the center of area. Yes. Sorry, I couldn't hear. Well, in this case, in this example that I'm showing here, I'm actually just trying to calculate on the sort of the inclined area. Of course, if I calculate for this horizontal area, it will be that area. So I could look at each different piece here of surface and calculate the force. In the example, I was just trying to concentrate on this inclined area. Okay? All right, if no more questions, then...
Sorry, I have one.
Yes?
Regular shaped area or maybe some oblong area?
It could be any shape. Yes, any shape. The shortcut that I'm showing here is particularly useful if you have a rectangle or a disc or something like that, where you have a formula for the centroid. But the most general way to calculate this is always going to be to integrate, because if you have a strange shape, it's quite hard to know exactly where the centroid is going to be. So that's the most general approach. That's why last class, we introduced numerical integration, which would be a technique that you could use for any shape that you have. You can find numerically that integral. And notice that this formula is independent of the angle. So if we have a surface that has this angle, suppose that the surface is some sort of rectangle. I'm trying to draw a little bit of perspective here, and this is the angle. Or if the surface is completely horizontal, almost horizontal, and just this is a very small angle, it doesn't matter. It does not depend on the angle. It only depends on the depth of the centroid, the pressure there, and multiplied by the area, and that gives the resultant force. Okay, so we'll do, of course, an example later on so you can see how this works. And let's move to another shortcut, shortcut number 2. Remember, I said we can calculate the magnitude of the resultant force by using the depth of the centroid. But the line of action of the force is not on the centroid. And the reason it's not on the centroid is because the pressure increases as you go deeper and deeper. And so the line of action of the force is somewhere below the centroid, because the pressure has a larger magnitude below than it has above. Does it make sense? So, in fact, the center of pressure is always below the centroid by a measure that we can calculate in terms of this equation, where I bar is the area moment of inertia about an axis passing through the centroid, and YC is so Y is, I am not using H here, I'm using Y, because, so suppose again I have my, oops, let's look at, let's try it again. I have my surface of the water here, and now I'm looking at an inclined surface from somewhere around here, and I want to calculate, and this is a sort of side view of the surface, and I want to calculate the resultant on this surface, and the centroid is somewhere around here. So now I am, instead of using H, so H is over here, HC, I'm looking at a slant distance from the surface, Y. This is kind of a coordinate that goes in the plane of the surface. And that's the coordinate Y that I indicate there. So Y of the centroid is this value here. And somewhere a little below will be the point of action of the resultant force. Because remember, the pressure increases as we go deeper, and so basically there's more pressure in the lower side of the surface as there is in the upper side, and so the resultant force acts somewhere below so there's F, and somewhere below here we have Y. P, I call it P for center of pressure. And this difference here, YP minus YC, this difference, how much below the center of pressure is indicated by the area moment of inertia around an axis passing through the centroid, divided by YC and the area. And so, for example, the moment of inertia for a rectangle, so this is only going to be useful for regular shapes, right? It's only useful for rectangles, triangles, and discs, and some regular stuff. Otherwise, this shortcut is not really that useful. And so, again, the most general approach is going to be to solve those integrals. And probably numerically is going to be the easiest way. Numerically integrate, and that's what one would do. You could have a little program if you do this like on a regular basis for designing, submarine structures. You would probably write your own little program to do the integrations according to, say, some CAD description of your shape, right? But for regular ones, like the ones that we can do in class for exam problems and so on, we'll use sort of regular geometries. And in the case of a rectangle, we know that the moment of inertia, the area moment of inertia, is equal to BH cubed divided by 12, where basically this is B and this is H in the rectangle. So this is one example where we can apply this formula quite easily. And in the back of the book and so on, you'll find similar formulas for a disk or a triangle, and that's about it. Anything else gets a little bit more complicated. Yes? The axis, so imagine, let me try to draw this in perspective. So it would be something like some sort of perspective, and the axis is passing through the centroid like that, so that basically imagine what the pressure is trying to do on this inclined plate is to make it rotate around that angle, right? So that imagine so if I look at the side again, it's some sort of torque around here, right? So this is what you're looking at. Let's look at an example immediately so this will be more clear. Here's the example. So we consider two volumes of water. One is salt water and one is fresh water, and these are separated by a wall. So how does this look? Say we have a wall, perhaps a concrete wall. Let's imagine a concrete wall. And on one side you have salt water, and on the other side you have fresh water. And the depth of the salty water is 7 meters. Then the question is to find the depth of the fresh water required to give a zero resultant force on the wall. So we don't know the depth of the fresh water. Let's call it H. But we want the forces to be equal on both sides of the wall. So we have some sort of force here due to the salt water. Let's call it Fs. And we have another force somewhere here, perhaps equal to a force of the fresh water. Let's use a little f here. And we want zero resultant on the wall, so we need Fs equal to f little f. A zero resultant on the wall. So now we use our shortcut number 1. This is a rectangular wall. I'm drawing a cut through this on the side, but it's a rectangular wall, so I'm just going to imagine a 1 meter depth in the direction perpendicular to the plane of the screen. And I can use a unit length in that direction. And so I can use my shortcut number 1, and the resultant force is equal to the pressure at the centroid times the area, so gamma of the salty side, and times the depth of the centroid on the salty side, that's the pressure at the centroid, multiplied by the area on the salty side. It has to be equal to gamma on the fresh side times the depth of the centroid on that side of the wall and the area on the fresh side. So those are the two forces. So now we look at unit length of wall in the direction perpendicular to our sketch here. And so we can calculate. We have to look up the gamma of salty water and the gamma of fresh water from some table in the back of the book or something, and I've already done that. So we have 10.1 kilonewton divided by cubic meter for salty water, and the centroid for a rectangle is just in the midway point. It's just the geometric center, and so it's 7/2 of a meter in the vertical direction. That's the depth times the area, which is going to be, for a unit length of wall, 7 meters times 1 meter. That's the area. And on the other side I have gamma of fresh water, 9.8 kilonewton divided by cubic meter, and well, we don't know the depth of water on that side, so let's just write h½ for the depth of the centroid on that side. And we don't know the area either because we don't know h, so h meters times 1 meter will be the area on the fresh side. So you can see our only unknown is h, and we can solve for h quite easily now. Just put those little numbers in the calculator and you can get h. And according to me, h is equal to 7.11 meters. You can check that. Just multiply these numbers, divide over by this, multiply by 2, take square root, and that's it. Yes? Question? Yes? You look a bit perplexed.
Yeah, I was just wondering if the overall the moment matter.
We haven't gotten to that yet. We're just looking at the zero resultant force. And the next question is, will the moment due to the fluid forces be zero when the resultant is zero? That's our next step. I left a little space down here to do that. So in order for the moment to also be zero, the two forces would have to be collinear. You kind of have a hint from how I drew this that they're not necessarily collinear. And you can imagine that if these depths are different of the two waters, the two salty waters on the salty and fresh water on each side, then the point of action of those sources is going to be different. The point of action is the center of pressure, and in shortcut number 2, we know how to find the distance between the centroid to the center of pressure, and so we can find the point of action of the resultant force for both cases. So let's look at the moments now. First, we're going to find the point of action. For the salty side, we find y, point of action, so let's call it yp for center of pressure, s for salty side, and that's equal to I of the rectangle divided by yc for the salty side CS, and the area, oh sorry, I think the area is down here, yes, the area of the salty side, and plus YC, right, we had YP minus YC equals to this, so I'm just adding YC on both sides of the equation to get to get that. And well, so this is a rectangle, so it's BH cubed divided by 12. So 1 over 12 times, let's just look at 1 meter depth again of the wall. So 1 meter times the h, which is 7, and that's cubed, divided by, this is on the salty side, so we know that the location of the centroid is 7.5 meters. And we have the area, which is 7 meters times 1 meter. And plus the depth of the centroid, which is 7.5 again, 7.5 meter. So we have everything. We just now can put this in the calculator because these are just numbers that we can obtain, that we can sort of calculate. And I've done this already, and I get 4.67 meters. And on the fresh side, I can do this exact same thing and find Y pressure, the center of pressure of the fresh side equals to, same equation, area moment divided by YCF for fresh, area fresh plus YC fresh. 112, 1 meter, and the height now, we just calculated that is 7.11. 7.11 meters from our previous results, cubed, divided 7.11 half meters, and the area, I don't have much space, 7.11 meters times 1 meter, and all of this plus 7.11 over 2, and again we have everything, and we can calculate, and somebody there is checking my arithmetic, and he agrees. For this one I get 4.74. So like we expected, the points of action of these two forces are not the same. So there is a moment. There is even though the forces are equal on both sides, there is in fact a moment, because the distance to the point of action from the bottom of the tank, well, we would normally want to calculate, probably we would want to calculate from the bottom of the tank, and you can remember this here is y, so it's measured from the surface down. This is a vertical wall, so it's measured from the surface, and you might want to, calculate that with respect to the point where this wall is actually fixed somewhere. So that would be from the bottom. I don't have space to do that, so we have to calculate the force, the distance to the both resultant forces from the bottom of the wall. But you can see clearly anyway that they're not collinear, because basically what I want you to notice is that this 4.67 is on the salty side, so it's measured from here to here, and this 4.74 is from the fresh side, so they're actually measured from different points. They're different reference points. It's the surface of the liquid on each case. So we do need to actually go that extra little final step and see what the distance is from the bottom. It might be that there's an extreme coincidence of geometry here, that when I calculate it from the bottom, they kind of coincide, but very unlikely. But that would be the correct thing to do, to look at the distance from the bottom. I just didn't leave enough space here to do that. You see? You all agree with that? Is that clear? Okay, good. Okay? It's pretty close. Did you? Huh? 0.04. It's pretty close, isn't it? So you have to do that extra step of looking at the distance from the bottom up. They're pretty close. So the moment is quite small, and you can see that this is not going to be a very difficult design situation for that wall. So we've used our shortcut number 1 and shortcut number 2 to calculate this, to solve this problem. This is a typical sort of problem that you can do on an exam or homework because you can't really do a numerical integration, but remember the most general way to solve this type of problems for any surface will be to do that integration. So shortcut number 3 is for the case of curved surfaces. You must have done one example, at least last lecture, for a curved surface, and you saw the sort of long but more general approach, which is to integrate. But here's a shortcut. So if you look at the horizontal force on a curved or inclined surface, that is going to be equal to the horizontal force on a projection of the surface, projection in the horizontal direction. I will explain further in a moment. And the vertical force on a curved or inclined surface is equal to the weight of fluid above. So let's explain that a little bit. So let's consider this situation which is on the sketch, where we want to calculate the resultant force on this curved surface here that is shown in blue. So we want to, to do that, what we're going to do is look at the equilibrium of forces for the volume of fluid that is contained in this, I'm looking at a cut, and I see this sort of curved triangle shape ABC, and I'm also going to consider the volume that is produced by this area multiplied by a unit depth in the perpendicular direction to the sketch. You see that shape is going to be a shape like this, sort of. That volume of water of a unit depth, we're going to look at a free body diagram of that. So I'm just going to draw the cross section of this area, and we have A, B, C. Now this is the fluid side, okay, just the volume of fluid, but we also have the wall, curved wall, and the forces, well, we have a vertical force here, FAB. We have a horizontal force here, FAC. We have the resultant acting here, and on the wall equal and opposite. Basically, this is what we're looking for, equal and opposite here, F. What do I call it? Just F. Okay, so I've separated the wall from the volume of fluid to obtain F. So we're isolating, to do this, we're isolating the volume of fluid ABC times a unit depth. And so you can see immediately from my picture here, by isolating the volume of fluid, that the horizontal force on this wall must equal the horizontal component of the resultant force, right? Immediately. So we have in the horizontal direction simply that, what did I call it, FAC is equal to, let me say, force horizontal And in the vertical direction, we have FAB. Oh, but let's not forget the weight of this fluid plus the weight has to be equal to the vertical component of the resultant. Now, FAB is the force due to pressure on this surface, which is basically only going to be a function of the depth of this line. So basically it's just this h here, the depth of this line AB, so it's going to be gamma h times area. So this force FAB is really equal to gamma times HAB times area AB, which is basically the weight of the column of fluid above. So let's look back to what the sort of short explanation said. The horizontal force on the curved, which is the horizontal component of this guy here, is equal to the horizontal force on a projection of the surface. Well, that's very clear here because this area AC is going to be equal to the projection of that curved surface in the horizontal direction. On the other hand, the vertical force on the curved or inclined surface is equal to the weight of fluid above it. And sure enough, we have the weight of fluid inside this little volume that we've isolated plus the weight of column above. So it's the weight of all the fluid above. That's the vertical direction. Clear? So that is for curved surfaces, our third little shortcut. So, let's see what time it is. Let's take a little break now, and in 10 more minutes we can continue with another final example on this before we continue to more new things.